Okay, great to be back with folks here in person. For those who are local and for those who are remote, at least to be able to give this from a somewhat more uh, appropriate setting and to be back in the swing of things. So I was leading this event at Banff on methodological innovation for agent-based modeling and accomplished a lot of good things, but it required a great deal of focus, and I appreciate all of your patience with that. I'm looking forward this week to really engaging with students here and in my other class. Okay, so we're entering a phase in the course where we're going to have a set of topics which are quite important for agent-based modeling, but supplement the somewhat more basic understanding of agent-based mechanisms with some additional material. And the first topic that I wanted to hit somewhere, and I figured I'd really address it here because of it has relations to topics we have talked about recently involving contacts between individuals, networks, and different types of networks and their impact on model dynamics, ABM dynamics. I thought I would deal with it here. And it has to do with scale-free models. Those present will recall that in past weeks, we had spoken about and actually examined interactively some ways in which elements of model structure manifest through networks in ways that shape model dynamics, responsive to the general principle that structure drives behavior. An important element of structure that we have a language to capture, we have mechanisms to capture in agent-based models is network structure, cellular structure. And that reflects different types of relationships. The notion of what a link is, a connection is, differs quite a lot by different subject areas or different areas of application. But it plays a big role within within many agent-based models, and I would say within a plurality, a very large fraction indeed. We had examined in this previous session, interactively, systematically, we had gone through a set of network types, from network types that were exhibited very local connections where individuals were connected with others nearby them in both a 1D context, ring lattice, 2D context, where people are connected with others in nearby two-dimensional space. And we examined that all the way to networks where people's connections to each other was completely independent of any sense of closeness. Probability of two people being connected in a Poisson random network was the same, some probability P, regardless of any sort of ordering or closeness of people. It didn't take that into account. And we saw some mixtures of the two in a form of a scale-free network, small world network, where it was mostly local connections, 95% perhaps, with some global. And we saw the dynamics induced by each of those network types in turn were quite different. And I won't elaborate, but we also saw it wasn't just a matter of just proportional to the fraction of one type of network or another. We saw that even a few global connections, a very small proportion of global connections in a small world network induced behavior more similar to what we see in random mixing. Not the slow spread, propensity to die out, the bottlenecks, et cetera, associated with very localized networks, but rather the spread diffusion across the network that we expect as characteristic of random mixing models where people interact more broadly. All it required is a small fraction of connections. It's almost like the small number of embers from a burning wildfire that can waft in the wind and seed fires around that can lead to massive spreads of fires very quickly, sooner than if they could purely locally spread. And there's other analogies, other applications that could be mentioned. So bring your heads back into that space. There is one type of network which I think I examined in a pro forma way, but really hadn't properly discussed. There's one type of network that isn't like the others in some very important ways. And there are ways that really lie in many senses close to the heart of agent-based modeling. They have to do with connection, yes, but they also have to do with heterogeneity and disproportionate effects of heterogeneity through multiple mechanisms as it manifests in emergent behavior. It's also a topic where we're dealing with distinctions involving heterogeneity, and particularly relational heterogeneity. Heterogeneity in terms of connections people have, in a way that's awkwardly explored only. And even there, only partially, by compartmental models, by lumped models that kind of lump people together into compartments. And this type of network is a scale-free network. Scale-free behavior, self-similarity, is a topic of great significance more broadly in the complex system science area. We see it in many types of complex systems. We see self-similarity in scaling laws, for example, invariance, no matter how far you zoom in. And some of you may be familiar with images from the Mandelbrot set or other fractals, which exhibit this sort of self-similarity. And we're going to see that sort of self-similarity, that sort of scale-free behavior with these sorts of networks. Behavior which gives them their name. So with that preface, I'd like to turn to some slides. And with some regret, because of the strictures of time, I'm not going to have a chance to interactively explore this today. If there's interest, we could do so in the lab session. But scale-free networks have so much to bring to the table in terms of sort of exploration of their theoretic features that I wanted to devote this session to them. So, worse when it comes to scale-free networks than to talk about some of the phenomena in the world that motivate their study. Over the past half century, researchers noted in a remarkable number of different areas of network application, where network structures, connections are present. And in many areas of health where similar patterns arose, where we had, for example, for sexual partnerships, many individuals having just one partner, but some individuals having much larger number of partners, and the numbers actually stretch out here along this axis so that you can't clearly see them. In empirical context, you can find numbers that are in the dozens here, number of partners in a 1-year period. And you can see for same-sex partnerships, one can see very high numbers. This is empirical data, so many of these seem to be zero cells. But the point is there's a long tail here. And there's a long tail in the context of most being low, but having a very long, so-called heavy tail, a very high number of potential partners further out. There's real heterogeneity in the number of partnerships by 2 orders of magnitude from 100 to 1. And if we plot this graph out, you'll see something like the following. If we plot a log-log graph where the number of sexual partners here on the x-axis is plotted, but the log of it, right? So here this log scaled plot, and so here, as you go out a fixed amount, it actually is multiplicative, right? Go from 10 to 100 here. That same amount out will go from 100 to 1,000 over here. And this is also log scaled, right? And what you see is a striking semblance to a line in this log-log plot, this log scaled plot on where each dimension is log scale. The fact that it's both dimensions that are large scale is very important. And here with same-sex partnerships over even longer scale. Now, you could be forgiven for thinking that that these are, sort of one-off curiosities or sort of quaint observations. But they do recur in a striking number of different areas. Contact patterns over wide ranges of scale. Contact frequency between individuals. Patterns associated with social connections people have and the number of connections they may have online. You may think about influencers who may be very, very far out in this tail, whereas most people have a small number of connections. Commercial transaction networks. For those from technical background, dependency graphs, whether it's in the business area, physical sciences, social sciences, health sciences, a staggering array of different cases. And some of our own data has viewed this, has seen this over significant scales, for example, in contact duration involving individuals. Now, again, you might say, well, okay, so that's a interesting pattern. It recurs. Well, what of it? Well, it turns out that it's really important for many phenomena, and certainly for contagion, spread of contagion, whether it's pathogen, knowledge, attitudes, beliefs, innovations, ideas, conspiracy theories, rumors, and other types of information. This marked set of patterns is extreme heterogeneity, but structured heterogeneity, where there's differences over orders of magnitude in some structured way, bears attention. And I want to motivate just a bit of a reflection here. If we consider the spread, let's say pathogen over a sexual partnership network, for example, over a bloodborne, maybe it's needle sharing in a bloodborne infection network. Someone with a high number of partners in this regard is simultaneously more likely to be infected by someone else, right? And they're more likely to pass the infection on to another person. They have large numbers of connections. They're like magnets for new infections, right? and they can disseminate it to very large numbers of people. So they are simultaneously attractors for and disseminators of, very effective. They can be super spreaders in this regard, right? And as a result of it, I hope it will make it plausible that, look, when it comes to the spread of infection of people out here or out here in the network, it may look very different from most individuals who are over here. For every one person down here, there may be 10,000 over here, but that single person may have a vastly disproportionate impact, may be able to keep the infection alive, an infection that would die out if the behaviors were restricted to this area of the network. And indeed, that's the case. For those who are health science background, interest in public health interventions, it bears noting that, when you see these types of disproportionate impacts on certain groups that are at once more vulnerable and inadvertently can lead to high amounts of spread, there may be certain types of targeted interventions that could be very effective and very cost effective. Now, today we're going to get into, what sort of networks account for these patterns. Why do these patterns arise? And as time allows, we'll also talk about, I'm not sure we'll have time to finish fully, but I'll at least walk through the basics of how to modify some equations in compartmental models to take those to account. And what we'll see is that it kind of breaks out of what we can effectively characterize in compartmental models, but in a way that'll be very instructive. Okay, so I want to introduce here, to explain these patterns, scale-free networks. Okay, and these are networks that will exhibit what is called power scaling laws. So, as a matter of notation that's going to follow us through this lecture, we're going to denote the number of connections of a given individual as K. So imagine K connections a person can have. Now, so they have ongoing set of K different neighbors that they can infect. It's important that's not merely contact rate. If that's a contact rate K, but it's all with one neighbor, it's actually going to defeat the purpose. It's that they have K different neighbors. Okay. And the hallmark of power law scaling here is that the chance of having K partners is proportional to K to the minus gamma. Now, you'll recognize that K to the minus gamma is the same as 1 over K to the gamma. And commonly, gamma is 2 or above. And so it rises, K to the gamma. If we consider the chance of having K partners being 1 over K to the gamma rises rapidly, right? It's like if gamma is 2, it's like 1 over K squared. So if we double the number of connections we're considering, going from 10 to 20 to 10, will be 1/4 of what is for 10. Number for 20 will be the probability of it for 20 will be 1/4 of the probability of having that many partners for 10. Excuse me, having 10 partners. It bears noting that for human sexual networks, you see ranges in this range, and for other networks, you'll often see different values of gamma being measured. It bears emphasis here that because this drops very quickly with k, again, if we consider 1 over k to the gamma, the denominator rises very quickly with k, and therefore the overall fraction drops markedly with k. What it means is most nodes have a small number of connections, small k. Small k is where most of the probability is concentrated. It's only a small fraction that have large k, but those fraction will end up being very important. And in fact, there's a heavy tail, and we'll see just how heavy that tail can be later. Okay, so let's talk about the features of power law scaling. I sort of gestured at it in my last slide, but I want to talk about it a bit more. So I said that, look, the chance of having k partners is proportional to k to the minus gamma. So by proportional, I mean probability of having k partners is just c times k to the minus gamma. And c is a constant proportionality, right? To make it add up to 1 across all k's. Okay, now let's consider going from a situation where we have k partners to a situation where we have alpha k partners. Maybe you want to think of alpha as 2, for example. So if we have 10 people with whom we have contact, and we consider the fraction of that many, versus 20 people with whom we have contact. Or, if you want, consider the probability that you have 4 connections versus 8 connections. So again, alpha k is double the number of k, right? So if we're assuming for our thought experiment that alpha is 2, going from 4 to 8, or going from 10 to 20, or going from, indeed, 50 to 100, the ratio is going to be the same, okay? And you can do out the math as to why that is. I mean, you substitute in alpha here, alpha k for k itself, and what you get is something with c times alpha to the minus gamma times k to the minus gamma, which is just p of k times alpha to the minus gamma. So in short, if you double the number, whether we're dealing with 4 connections going to 8, and we consider the ratio with 8 compared to 4, the ratio of the number of the probability of having 8 connections compared to the probability of having 4 connections, or we consider the probability of having 20 compared to 10, or the probability of having 100 compared to 50. The ratio of the two, P of alpha k, which is this, divided by P of k, is always equal to a to the minus gamma. And what's notable is this does not depend on k. It's independent. It's always the same. So having k connections versus 2k, the ratio of people with that fraction of 2k connections compared to k connections is always the same, regardless of k. P of k looks the same however far out we go. It goes down by the same speed of having it at k versus 2k. Okay, and that leads to large numbers of connections extending. It leads to connections extending out here. Most people have very few connections, but there are some, no matter how far you go out, if you go out to 15, the probability of having 30 compared to 15, that ratio is always the same as it was going from 5 to 10 or going from 3 to 6. Now, sort of power law scaling, this sort of scaling where if we scale by a factor, let's say double the number of connections we're considering, we're multiplying the probability, the resulting probability gets multiplied by a constant, independent of k. We see that from many sources. And one common source is dimensional structure of a situation, just the dimensions involved. We can also see it for processes of preferential attachment. the influencers who have large number of connections are more likely to be discovered, be recommended by YouTube's recommendation system or recommendation system on Instagram or whatever other channel you have with public networks, and therefore more likely to get new users, right? Web pages with lots of connections to them are more likely to be discovered and to get new connections. We call this preferential attachment. And it can occur in the commercial domain. It can occur in the health domain. It can occur elsewhere, social sciences, many different areas. In computer science, and computer systems. It's notable that we have a reinforcing feedback here. The more connections an individual has, the quicker they accumulate new connections. Now, let's talk about that characteristic straight line we noted earlier from empirical data, this sort of line that we showed here. Where does that come from? Well, it comes out of the mathematics, right? Look, you recall that the probability of having k connections in this one of these scale-free networks, whose probability of having k connections is given by this power law, is proportional to k to the minus gamma. Well, if you take the log on both sides, right, log of p of k on the left, log of this right-hand side, this is what you get, right? And just take into account the fact that the log of, a times b is the log of a plus the log of b, right? And of course, if you have log of c to the minus gamma, that's the same as minus gamma times log of k. So you combine these, and this is what you get. You notice the key point is that this relates to log k. That's the vertical axis here. Log p of k to the horizontal axis with log k, right? If one doubles log k, then we'll go down by here from v log k to v log 2k, or 2 times log k, right? Well, we'll go down by a constant amount here every time we double log k. Excuse me, every time we go up, we increment log k by a fixed amount. Excuse me, not double. Every time we double k, and therefore change log k by a fixed additive amount, we'll go down by gamma, right? The intercept is log c. When k is 1, this term disappears. We'll have log c, and then we just go down. This is just the slope minus gamma. I think everyone recognizes this. And I mentioned this feature of power laws, right? If gamma is 2, I argued that doubling k leads the ratio of people with 2k compared to k connections to go down by 2 to the minus 2 or 4 by factor of 4. If gamma is 3, doubling that number of connections, say from 4 to 8, or from 10 to 20, will lower the probability of having 2k connections compared to k to go down by a factor of 8. In other words, the probability rate is multiplied by 2 to the minus 3. So this is where this law comes from, and you should have that sense of like, okay, gamma of 3 is going to have this effect of doubling leading to 1/8 the probability of having that number of connections. Gamma of 2 is going to divide it by a factor of 4 when we double, etc. Okay. So if we have these scale-free networks, as I noted, the vast majority of people are going to have fewer connections, but there's going to be some individuals with larger number of connections. And I argued earlier from this seat that those people really matter. They're vulnerable to infection, and given infection, they're in the inadvertent role of being subject to spreading it very widely. And these power law relationships can exist over wide ranges of scales, leading to really disproportionate impact of individuals further out here compared to most individuals. And this can very significantly affect the spread of infection. It can lead an infection to remain present that otherwise would die out. The fact of this heterogeneity. Okay. Now, there's some mathematics that we could do that would let us derive this constant of proportionality. We need, remember, for P of K, that's a probability mass function for different Ks. It's given by this. It bears noting that this is 1 over K to the gamma. So we generally rule out K equal to 0 as being considered here, because that would lead to 1 over 0. And so we'll consider K 1 and larger as part of the probability. And we can figure out by requiring this to sum up to 1, as is the requirement for a probability distribution, we can figure out what K must be. And here we can write an expression for it, but it turns out that through an integral approximation, some of you will be more attuned to this than others, we can approximate this as this integral, and we can integrate it and basically find a form where P of K equals gamma minus 1 quantity times K to the minus gamma. So this is just a constant of proportionality. It's just what this needs to sum up to 1, right? And I won't go into the details of this derivation, other than to note that we often want to refer to this as a distribution, and therefore it's good to know the constant of proportionality. Okay, now what's more significant is having done that, we can having defined this as a proper probability mass function for different K, we can get a probability given, for a given value of gamma. We can actually do it for gamma in general by taking our probability, and we can take the mean of this number of connections. So each number of connections, K, has a certain probability of being seen in the population. So we can ask the question, what's the mean number of connections in the population? I said earlier that there's a lot more people with fewer connections than with larger, but there are some people with lots and lots of connections. There's a heavy tail. So what's the mean? What's the mean number? Well, we can calculate it, right? Given that we have this as a probability distribution here. I've taken the liberty of calling K X, and we can take the mean of the integral of X times P of X dx. So here we're taking the mean number of connections. This is the number of connections. This is the probability of having that number of connections. And what we find is that it's given by this. Gamma minus 1 divided by gamma minus 2. So gamma minus 1 can be seen as coming from there, divided by gamma minus 2. Now, this is interesting. Among other things, it suggests that if gamma is 2 or less, this doesn't exist as a mean, right? It turns out it's infinite. It has no mean. If gamma is over 2, this will have a mean. Let's suppose gamma is 3, right? This would be 3 minus 1. That's 2 divided by 3 minus 2. That's 1, right? So the mean would be 2. 2 connections. If gamma were 2.5, this would be 1.5 over 0.5, right? 2.5 minus 2. So the mean number of connections there will be 3. The mean number of connections in the population. Now, there'll be some people with many, many times that number of connections, but they're comparatively few. Let's talk about variance here. Now, this one is really quite interesting, and it's impactful for reasons we'll get to particularly. So the variance in the number of connections within the population is given by this expression. Excuse me. This is the second moment here. I calculate the second moment, and then I take the variance as this second moment minus this squared. That's the expression for the variance. And you get this. And what's notable is that this term here is only exists. It's only valid. This only converges if gamma is greater than 3. Right? If gamma is less than 3, that would imply it won't drop off. So if gamma is greater than 3, it drops off faster, right? The faster gamma, the larger gamma is, the faster it drops off, right? Remember, it goes down by, where's a nice expression of this? It goes down by k to the minus, or it's proportional to k to the minus gamma. So if gamma is larger, as k rises, the probability of having that number of people with k connections drops off more quickly. Bigger gamma is, the faster the fraction of people with k connections drops off as you increase k. Put it another way, if gamma is small, there's a lot more people with larger numbers of connections than if gamma is large. If gamma is large, most people have very few connections. So here, this expression is only valid if gamma is greater than 3. If gamma is less than 3, the variance doesn't exist. Okay, now you may be shrugging your shoulders and saying, well, okay, that's nice. Thank you for telling me that. But like, what's the significance of that? Why does that matter that the variance doesn't exist? Well, it matters a great deal. And I'm going to tell you the punchline. And as time goes, as time allows, I'll lead you through some of the derivation. The basic deal is that the variance is going to have a huge impact on the speed of spread of this infection. And what we're going to see at the end is that the basic reproductive number in a network where we have scale-free connections is given by this, by a term involving the mean plus the ratio of the variance to the mean. And this ratio does not even exist. It goes to infinity as we approach a gamma of 3. So in short, if we have a gamma that's too small, that's less than 3, what that suggests is that we can have an arbitrarily large number of reproductive number as we approach 3 from the upper side. If we have gammas that are larger, the number of connections drop off more quickly as k rises, and we will have reproductive numbers as gamma rises that are successively smaller, where this ratio is less big. But it's really with small gammas. This ratio gets very large and then fails to exist. Okay, so I'll talk a little bit about it, although we might not have a chance to fully go through all aspects of it. But this is a fields course, and this is a lecture which involves some technical content. And I'll be going fairly quickly through it, but hopefully you'll get some key ideas, even if you miss some of the details. So what we're going to do here, we're going to build on what we've seen here to reason about spread of infection in a compartmental model. Now, the goal here, this might seem odd in a class on agent-based modeling to be talking about a compartmental model, but bear me out. The issue is that we're going to talk about compartmental models and their limits here. We're going to talk about compartmental models where we try to characterize the rate of spread within the compartmental model. And what we'll find is that there's a limit to what we can represent. And if we have scale-free networks with smaller gamma, we will run into an inability to effectively express them in this compartmental context because the heterogeneity will be too large. And there'll be spread that is infeasible to capture effectively. So let's talk about this. Okay, so some of you may be familiar with compartmental model, with stock and flow model. And you may remember that if we have a compartment here, those who have seen it before, the rate of change of I is given by the inflows minus the outflows, right? This is the inflow here. This reflects infections. Each susceptible has contacts with C people total. A certain fraction of those connections are assumed to be with infectives. So if a susceptible has contact with 100 people per day, and if 50% of the whole population is infected, we assume that, so that's 0.5 of the whole population is infected. You assume that of the susceptibles connection, 100 times 0.5 or 50 of their connections are with infectives. And each of those connections with infectives we treat as inducing a certain probability called beta. Maybe it's 0.2, 0.02, or say 0.2, right? So 50 times 0.2 is 10 as a here for this term, and here therefore they'll have a certain high probability in that case that a given susceptible is infected. If this were 0.02 beta, they would have still a high chance, chance per unit time of 1. If beta were 0.01 and we had 50 infectives each susceptible comes into contact with, they'd have a probability of 0.5 per unit time of getting infected. And then we have the outflow here. So this is from the inflow, this guy here coming in and then leaving I over D. Forgive me, those who have not seen this before, but some people here will be familiar with this. Okay, now what we're going to try to do, and we're going to run into the limits of it, but we're going to try, is we're going to try to take this term and take into account heterogeneity in terms of number of contacts. So we're going to break the population up into groups according to the rates of contacts. We're going to have people with infectives with K connections. We're going to have susceptibles with K connections. And C here will differ based on the number of connections that they have. Are we okay with this? Okay. So we're going to divide up people based on the number of contacts per unit time that they have. So I2, for example, will denote the number of people in the population who contact 2 people per unit time. We're basically dividing I and S up into subpopulations that have a certain number of connections, K. Okay? Okay. So here we go. And we are going to take this and we're going to replace it by this. Okay. So here's our I sub K is the number of infectives with K connections. S sub K is the number of susceptibles with K connections. Now, the number of susceptibles with K connections, we may not know everything about them, but one thing we sure do know is that they have K connections per unit time. So their C is K, right? Someone who's susceptible, by definition, they have K connections per unit time. We know their C is K. That's why we're breaking them up into this. And then here, as our first attempt, we're asking, well, okay, of all the people in the population, what fraction are infective? There it is. Look, there's people who have 0 connections, I sub 0. There's people with 1 connection, I sub 1. People with 2 connections per unit time, I sub 2. We have to total those all up to get all number of infective people divided by n. That's the fraction of people in the whole population that are infective, right? And then beta. So this is I over n is just this term because we have I broken up into contact groups. C is K, right? Beta is, well, we put a couple other factors there, including this ratio between rate of contact and C if they're not the same. Okay. So here we go. So we have this. The problem is that we haven't actually done justice to these terms. Amongst other things, we're assuming that if we have 10 connections per unit time, that they're equally spread among anyone in the population, right? This is the fraction of all people in the population who are infected. In fact, if we have a certain number of connections, chances are they're more likely to be with high contact people than with low contact people, right? If we sample connections in the population, that's different than sampling people in the population. A large number of connections in the population might be had by few people. Okay, so that's one issue. The second issue is people with large number of connections are more likely to be infected. So not only are connections disproportionately with people with larger number of connections, because that's who's having connections, those people are more likely to be infected. So we're more likely to have exposure to them. This was a good first attempt, but it's assuming that our connections are distributed evenly with people across the population. We should be distributed evenly with all the types of people who are having connections across the population. So we're going to do that. Okay. So this is our revised formulation. So look, we still have this basic deal. We're dividing the population up by the number of connections. But here's the kicker. This term here, which at first looks fearsome, is going to take into account the fact that when we have connections with people, it's more likely to be with someone who has a large number of connections, because that's who's having connections in the population. So this here is the total number of contacts per unit time made by infectives. Note the J in front. Before we didn't have a J in front, right? But we know I sub J has J connections, right? That's what makes them I sub J, is that they have J connections per unit time. So if we're thinking of ourselves as having a connection in the population, it's more likely to be with someone with a large number of connections. More than that, this is the number of connections across the entire people. This is the number of connections with infective people in the population. And here we're taking the fraction of connections that are with infectives. That's what this ratio is. This is the total number of connections, right? People in group N sub j, total number of people with j connections. They have j connections per unit time, so they contribute j connections. Those with N sub j, another group with j plus 1 connections contributes j plus 1 connections. So this here is the number of contacts per unit time made in the whole population. This is the number of contacts per unit time in the whole population made with infectives. That's what the numerator is here, right? If there's someone in the population who has 0 connections, they're going to be contributing 0. So they can be infective or not, but they're not going to be spreading infection, right? If someone here has tons of connections, their being infective is going to make more of a difference because they're going to be contributing across many connections. Okay. So here, this fraction is the fraction of connections in the whole population that are with an infected person. Do you get that point? And it's skewed towards those. It recognizes the disproportionate impact of those with large numbers of connections. They see more people, and they're more likely to be infected. Okay. Now, those with the background in communicable disease modeling may be able to recognize that this term here is what's called the force of infection. This is our chance per unit time that a given susceptible will be infected. Maybe it's 10% per week that is susceptible to be infected. So this is the force of infection for a susceptible. Now, it turns out that this can be reformulated for a SIR type of model. If we have this, we can reformulate it algebraically to something of this form. Here, this is like a SIR system, but we're considering force of infection and how it changes over time. And here, the basic reproductive number is given by this ratio. This is basic reproductive number is the number of people infected by an index of first infective in an otherwise susceptible population. And it is proportional to the ratio of this to this, okay? And times d, the duration of infective, so times this beta, this chance a given contact will transmit infection. So we have each infective as having this many effective contacts per unit time times chance per unit time, chance probability for each one that they transmitted infection. And they have that going on across d units of time. It's the product of all of these that gives the number of people they infect per unit time in an otherwise entirely susceptible population. This is the number of people that infect over the entire course of their illness, hence the D. Now, again, we're running out of time here. I will just note that this ratio that comes from the reformulation, we can engage in some algebraic manipulation of it. So we can re-express it as this minus this plus that. So these two are the same. Could just subtract this off, add it outside, and put it over the expected value of J. If we do that, that's going to allow for some simplifications. You may recall from our earlier discussion this identity that the variance is equal to the expectation of j squared minus expected value of j squared. And as a result, we can express, given that this is the variance, we can recognize that this term is just this one. It's just this guy here. So this is variance squared. And this term is the mean squared. So this is just boils down to this. The mean plus the variance over the mean, the ratio of the variance and the mean. And that's why this is where we're going. Yeah, I showed that to you earlier, a sneak preview. So what is this saying? Well, look, if we reformulate this, here we have something that is like, this is like our C term, okay? This is our C term. And what I'm saying is that this term, if we express it, it's equal to this sum. So in a compartmental model, if we wanted to capture the effects of scale-free networks, we could do so by making C in that network, making the contact rate in the network, this one right here, be equal to the mean number of connections plus the variance in the number of connections divided by the mean. But as we've seen, this ratio does not exist for gamma less than 3, 3 or below. This ratio only exists for gamma above 3. It blows up. It becomes huge as gamma goes down towards 3. Below 3, it doesn't exist. And the implications of this is that for a scale-free network with a sufficiently large population, where we have this as the basic reproductive number, this number will actually essentially always be greater than 1. And moreover, if the gamma associated with a scale-free network, this gamma here, with how quickly the number of connections drops off as we consider more and more connections, the probability of having how quickly the probability of having those connections drops off as we increase the number of connections. As if we consider gamma above 3, but getting closer to 3 and below 3, really this ratio does not exist. This ratio here. That means the variance in the degree distribution, and indeed the basic reproductive number, goes to infinity. It can spread extraordinarily quickly within such a network. People with large number of connections will disseminate it very quickly, and they'll spread it to other people with large number of connections. And so this ratio will no longer exist. With a large population, even if gamma is greater than 3, R0, the basic reproductive number, will still be above 1. And I believe, if memory serves me, it's because this ratio will be above 1. And therefore, the disease will tend to remain present in the population with a scale-free network. A scale-free network tends to lead to persistence in the infection within a population or of contagion in general, even though most people may have low number of connections and allow it to die out. Those with larger number of connections can keep it alive with a large enough population. So scale-free networks have this disproportionate impact on contagion spread and contagion persistence. They can lead to persistence of pathogen that would otherwise die out, and they can lead to massive growth, massively fast spread when the number of people with larger number of connections is sufficiently large, or the proportion of people with that many of connections is sufficiently large compared to those with smaller connections. It can spread extraordinarily quickly. In these contexts, trying to characterize it by force-fitting it into a compartmental model, by adopting a value for C equal to this proportion is not a viable strategy when we have gamma less than or equal to 3. We need an agent-based model to characterize that. And frankly, to characterize interventions, to be able to examine targeting interventions for certain core groups, individuals with greater number of connections, to undertake connection-informed intervention strategies like such as contact tracing or support groups. It behooves us to represent networks as well. Okay, I'm afraid we've gone beyond time here. I know this was awfully fast material in terms of its analytic content, but I hope you can take those points away from it, these high-level points about the disproportionate impact that heterogeneity in contact patterns can make in the spread of contagion in a population, including the persistence of that contagion and the speed of spread of that contagion. Thanks very much. And I do have a faculty meeting today right after this presentation, but I will look forward to seeing people on Wednesday. Thanks very much.